Welcome back to Math 103. This is video number 19 on apportionment. At last we arrive at the method which is actually used to apportion the U.S. House of Representatives and has been so used since 1941. The other three methods we've discussed in this chapter have also been used at some point in American history. The current stretch of time from 1941 to the present is rather a long time for a single method to have been in use. The Huntington-Hill method is another modified divisor method, and of all the methods we've discussed, it most closely resembles Webster's method, because Huntington-Hill will also round each quota either up or down, except that the modified quota is not rounded in this new method to the nearest integer. Instead, it is rounded according to a separate rounding rule. It's rounded according to the Huntington-Hill rounding rule, which takes a little work to understand. Here is the mathematical statement of the Huntington-Hill rounding rule, and if this puzzles you at first, don't worry, I will explain it carefully and give examples. Now, for a quota that we're going to call Q, that's just a symbol that represents however much the quota is, whether we're talking about a standard quota or a modified quota, the question will be, does Q get rounded down or up? And whatever that quota is, we're going to let L denote its lower quota and U its upper quota. So you've already computed a standard or a modified quota. It has a lower quota and an upper quota. Now, we ask, is this number Q less than the following strange item, the following strangely computed number? Multiply this L and U together and take the square root of that whole product. If the quota is less than this strange number, it'll seem a lot less strange when we do an example, don't worry, but if the quota is less than this funny number, then we round Q down. That means down to L. If Q, however, is greater than or equal to this strange square root, then the rule is we round Q up. That means round it up to U to find the rounded quota. I realize this is quite a lot of symbols, quite a lot of letters, and not enough concrete numbers. So let me explain it another way and then do some examples. So first, a translation of that mathematical statement into English, or at least something resembling English. So in Webster's method, that made perfectly good sense because we rounded in the completely conventional, familiar way. The cutoff value for rounding up is the midpoint between lower quota and upper quota. All right, so if you're deciding whether to round up or down, you're essentially comparing the number to L plus 0.5. Right? If you have a number, if you have a quota that's 2 point something, then you compare it to 2.5. If the quota is 7 point something, you compare it to 7.5. If the quota is 129 point something, you compare it to 129.5. So this number that's halfway between lower quota and upper quota is just the average of those two numbers. The halfway point between 7 and 8 is 7.5. 7.5 is just the average of 7 and 8. Okay? That's officially known as the arithmetic mean. So what's going on in the Huntington-Hill method? Well, by contrast, instead of comparing to a cutoff for whether you round down or round up, instead of the boundary being lower quota plus 0.5, so think 7.5 as the halfway point between 7 and 8, instead we compute this number, the square root of, for example, 7 times 8. So this number, this seemingly strange number, is officially known as the geometric mean of L and U. So if our quota is 7 point something, then we compute the square root of 7 times 8, and we see if our quota is greater than this number or less than this number. If it's greater than, or in fact greater than or equal to, this number, we round up, and otherwise we round down. So now let's look at a numerical example. Suppose that a state has a standard or modified quota of 3.49. Right? We do our computation of standard quotas or modified quotas, we come up with 3.49. So in Webster's method, 3.49 is rounded to the nearest integer, and that means down to 3, because we've really compared 3.49 to 3.5. Right? That's what we really did when we decided whether to round up or down. Webster said compare 3.49 to 3.5, and because it's less than 3.5, we round down. Had it been equal to 3.5 or greater than, we would have rounded up. So the comparison is to 3.5. That's the cutoff for rounding one way versus the other. By contrast, in the Huntington-Hill method, we compare 3.49 not to 3.5, but instead to the geometric mean of 3 and 4. We compare 3.49, our quota, to the square root of 3 times 4, and that happens to equal 3.4641. So Huntington-Hill says for a quota between 3.3 and 4, for any quota that's 3 point something, you compare it to 3.4641. That's the cutoff for rounding one way versus the other. One way instead of the other. Right? So here the quota of 3.49 is greater than the Huntington-Hill cutoff, so the Huntington-Hill rounding rule says round up. Right? Our quota is greater than the rounding cutoff, so round up. This is a little bizarre the first time you see it. What we're saying is 3.49 is greater than the rounding cutoff for Huntington-Hill, even though it's less than the usual rounding cutoff used by Webster. If you think this is a little odd, you are in very good company. This new notion of rounding does take some getting used to. So before going on to the next video, let's practice this. Consider a state whose standard quota in an apportionment problem turns out to be 2.46. So here's a question for you. Using the Huntington-Hill rounding rule, will that 2.46 be rounded down to 2, or will it be rounded up to 3, and how can you tell?